Hey there, fearless AP Chem students. We are going to get into chapter 7 here, which talks about the electronic structure of atoms and the periodic table and its patterns, basically. So, the reason we're talking about this is because so much of our concepts in chemistry are built off of the idea of, or they're dependent on the idea of how atoms are structured, especially the electronic structure within atoms, which is kind of where the electrons are and how the electrons are structured and how the location of the electrons in behavior of the electrons influences each other within the atom and then outside of the atom, of course. So all of these, like this structure and the trends within the periodic table, they just influence so much of the rest of the chemistry curriculum. We just build upon these ideas, and all of these ideas in AP chemistry are kind of like synthesized or brought together by electronic structure in the periodic table. So we're going to tackle this. And hopefully in doing so, we can kind of build upon it, and all of the other concepts that we talk about are just going to make more sense because they are tied to the periodic table and this idea of structure within the periodic table. Okay, so with that said, let's talk about why are electrons important to chemists. This would be a good time to pause the video and just kind of think to yourself for 30 seconds. Why are electrons important to chemists? And hopefully what you have listed inside your brainstorming is so much of atom behavior is guided by electrons. The way atoms bond to each other is dependent on electrons. The way atoms behave when they're by themselves is guided by electrons. The way that atoms interact with things around it, it's all driven by electrons. And so in order to, understand and build models and be able to predict all of these things that are going to happen, we have to understand electrons, because electrons are what is driving all of these other things. And much of our knowledge of electron behavior comes from kind of surprising areas. Electrons are strange little beasts. They are super small. They are virtually massless. They're not actually massless, but when you take their mass into consideration, with other things around them, like protons and neutrons, their mass doesn't add anything significant to the mass of the atom as a whole. They're highly, highly charged. Even though their mass is, to the 3 or 4 orders below the mass of a proton, its charge is right there, one-on-one with a proton. And so they're extremely charged little beings. And on top of that, they move incredibly, incredibly fast. And if we are going to predict within any amount of certainty where they are or where they're going, we almost have to sacrifice one or the other, which we'll talk about in a little bit. And so electrons are very strange things. They're not like a golf ball or a bowling ball that we're used to dealing with in our macroscopic world. They're going to behave very much differently from those macroscopic spheres. And so they're really hard to study. All of that to say, they're extremely hard to study. And so instead of directly observing electrons, most of what we know about electrons comes from deduction. So we see something happen and we deduce back to why it has occurred. Another source of our knowledge of electrons is actually light. So before we get into electrons and the electron structure on atoms, I want to take a minute and talk about light. So here's how this all happened. If we talk about the development of the atom, what we see is, a very periodic succession of knowledge and understanding about the atom until we got to electrons. And what happened is we got to electrons and we kind of hit this wall of understanding of what atoms were and why they behave the way they behave, and a bunch of this phenomena that also occurred. We hit this wall, and we really didn't, and I say we very generally, I would love to be in this camp of scientists who made all these breakthrough theories. So I'm going to say we as a human race didn't really progress through that wall of understanding until we, as a human race, made some breakthroughs in light. So let's back up a little bit and talk about light so that we can understand kind of this context and how they got through these breakthroughs. So light, as you may know, is both electric and magnetic. It has an electro portion of itself, and then it has a magnetic portion. If you take physics, which you should, you'll study light a little bit, and what you'll see is there's actually two waves that kind of move forward together, and those two waves are perpendicular to each other. So as one wave is moving forward up and down, there is this second portion of the wave. Let's see if I can draw this. That is kind of moving. I don't know if that's very accurate. Let's pretend it is. Okay, anyway, as one's moving up and down, there's a second portion of the wave that is moving forward, but it's going front to back at a 90-degree angle to this other portion of the wave. So there's an electric and a magnetic portion of the light. So we call it electromagnetic radiation. Light is a very, very small portion of electromagnetic radiation. As you vary the wavelength and the frequency of electromagnetic radiation, you get different types of electromagnetic radiation. So on one end of the spectrum, when we have a very long wavelength, very low frequency. So by long wavelength, I mean like it could be on the scale of the United States of America. Like 1/2 of a wavelength could cover our entire country. And this is what we call, a good example of this is broadband radio or long form radio, something like that. So there are hobbyists. My grandpa was one of them, and they build their own radios in their basement. Yes, my grandpa did this. And then he would sit in his basement and he would kind of tune his radio and try to find other people that were on these frequencies with him. And what he found sitting in his basement in Michigan is he could communicate to people in California. He could communicate with people in England, but he couldn't communicate with people anywhere in between. He couldn't talk to someone on his radio who was in Ohio, really close to him, because his wave would go up and then it wouldn't come back down again until like half the country or the whole country over. And so all of those people in between his wavelength were just missed. So it has an extremely long wavelength, which means low frequency. And then as you go over, you start hitting things like TV, radar, infrared rays, and then here is where light is. So light, we typically measure light in nanometers, and this is what you've seen in the in those labs that we did with the spectrophotometer. Is we would set our wavelength to like 630 nanometers or something to that effect, because we're choosing one of these wavelengths of light to shoot through our substance in the spectrophotometer And so we're going to measure that wavelength in nanometers. So wavelength of our like broadband radio, we would probably measure that wavelength in meters. Light has a fairly small wavelength, and we would measure that in a nanometer. So if you think of a meter stick, you could fit 1 billion complete wavelengths of any given light inside that meter stick. So in our first lab in investigation 1, we measured how much blue dye would absorb of 630 nanometers. So you could fit 630 billion wavelengths of that light that we tested in 1 meter stick. That's kind of the scale that light's on. So infrared is going to be on the long end of our visible light spectrum, long wavelength. Ultraviolet is going to be on our violet or our shorter wavelengths side of our visible light spectrum. Okay, so as we keep going over and our wavelengths are getting shorter and shorter and shorter, we hit things like X-rays, even ultraviolet light. Some ultraviolet light is non-dangerous to humans, but there are a lot of ultraviolet wavelengths that are extremely dangerous to humans, and that's why we wear sunscreen, right? Right, we all wear sunscreen all the time, yes. Okay, and as you keep going over, our wavelengths are getting shorter and shorter and shorter, and we hit X-rays and we hit gamma rays. And that's those are kind of the very familiar examples off of the electromagnetic spectrum. So when we're talking about light, I don't want you to take light and separate it off and think of light as this like, one special thing that is set apart and unlike anything other. It's actually very common. It's actually a very common form of radiation. It's just a very common form of radiation that's within a very, very specific set of wavelengths, and that gives us visible light. So visible light goes from about 400 to 800-ish. So 400 to 800 nanometers is what our eyes can detect. And anything longer than that or shorter than that is still present. Our eyes just can't detect it. So when we are talking about light, there's a couple different characteristics that we reference in order to characterize the light that we're talking about. And we've talked about one for sure already, and that would be wavelength. So wavelength is going to be represented by this symbol. This is a lambda symbol. It means wavelength. Okay, wavelength is literally the measured length of a wave. So it's going to be measured in some sort of meters or prefixed meters. So it could be meters, it could be micrometers or micrometers, it could be nanometers, it could be femtometers, it's going to be, or it could be kilometers, kilometers. So it's always going to be a length, always going to be measured in meters. When we look at a wave, usually we look at it from the point of the origin. That would be this line. And then a wave is going to look something like that. So what I've just drawn is called a transverse wave. There's other types of waves, like sound waves are not a transverse wave. Sound waves are a longitudinal waves, and longitudinal waves have all the same characteristics. But if you think about a slinky, part of that slinky can be compressed and part of that slinky can be stretched. And so So that would be more of what a longitudinal wave is, which is what a sound wave is. But since we're not talking about sound waves, we're talking about light waves. We're going to stick with the transverse wave drawing. Again, if you love waves and you want to talk more about waves, take physics. They talk about waves a lot. All right, other characteristics you should know on our drawing. So we have our origin, that's the line that goes through the middle. We also have the top of a wave, which is called a crest. We have the bottom of a wave called a trough. From the origin to the crest or the origin to the trough, that would be called the amplitude. Maybe I should write some of these words for you. Crest, trough, amplitude. Okay, and then the wavelength is going to be the entire length of a wave. So you can measure that from any point on the wave to the identical point on the next wave. You just have to be a little careful. So if let's say we start from this point, this little purple point, a common mistake is going to this point on the wave, but notice it's not an identical point because at my first purple dot, the wave's going up, and at the second purple dot, the wave is going down, which means it's not the identical point. That is actually half of a wave, not a full wave. You have to go to the identical spot on the next wave where the wave is going back up again. Here's where our second wave would be. Okay, so this distance from one spot to the identical spot is called wavelength, and that is how we measure a wave. You can also go crest to crest, that would give you one wavelength, or trough to trough would also give you one wavelength. Okay, so we have crest, trough, amplitude, origin, wavelength. Another characteristic you should know is frequency. Frequency, ooh, that was decent. Is this little symbol. It's a nu. What I would do at this point in time is go Google what the nu actually looks like, because that is not awesome. When I draw a nu, it usually turns out to be kind of like a cursive V, something like that. Okay, so this is going to be our symbol for frequency. And frequency is how often the wave occurs. So if I ask you, what's your frequency of grocery shopping? I'm asking you, how often do you go grocery shopping? Do you go once a week? Do you go every day? Do you go once a month? And so when we're talking about the frequency of a wave, how often does a wave happen? We're going to talk about a number of waves that occur, or a number of waves that pass a certain point in a given amount of time. So what we're looking at is the number of waves per unit of time. Now, because we are scientists, and when we deal with our field, we often shorten things up so that we don't have to keep writing them over and over and over. And so a lot of times you'll see this unit written as 1/seconds. And so the number of waves is implied. Or you can write it as the inverse of seconds instead of writing it as a fraction. That fits more nicely into a typed line or a typed sentence. In industry that talks about frequency, you won't actually see waves per second or 1/seconds or the inverse of seconds. What you'll see is Hz, which is a hertz. And it means the exact same thing. 1 hertz is 1 wave per second. So if I give you a frequency of 7.4 negative s to the negative 1, you can also write that as 7.4 hertz. I think hertz is a lot more convenient for certain industries to write and to say. For us, though, because we deal so much in conversions out of one unit into one unit, it's actually a really cumbersome thing to deal with, because every time you write hertz, you have to rewrite it as 1/seconds before you convert it. You can convert it out of seconds or into seconds or whatever you're trying to convert. So I would encourage you not to use the unit hertz for the sake of conversions and thinking in terms of dimensional analysis and conversions. Okay, last thing, the last characteristic that we need to talk about would be speed. So speed is going to be a C. That is its symbol. It's the speed of a wave. And so it's literally how fast is the wave traveling. Now, when we talk about speed, we're going to talk in units. Like if we're talking about the speed of your car, I'm going to say, what's the speed of your car? And you're going to tell me 25 miles per hour, because I am a responsible citizen and I always drive the speed limit through neighborhoods. Okay, 25 miles per hour. What that is it's a distance over a time. So we don't use miles in science, we use meters. Sometimes we use hours, but in chemistry, usually we use seconds. So our units of speed are going to be meters per second. And so now what you can do, we will talk about speed a little bit more. Hold on to that thought. But I want you to look at what we have. We have wavelength, frequency, and speed. And those three can be used to convert in and out from one another. So I want you to think for a second. Now would be a good time to pause this screencast. How could you use wavelength and frequency to calculate speed? Pause here. Okay, and what I hope you saw was if we take meters and we multiply it by 1/seconds, we're going to get meters per second. And so there is your formula for calculating speed of a wave. Meters, which is wavelength, times frequency, times 1/second, which is frequency, is going to equal speed. All right, here's the deal in physics and chemistry. You can either memorize or derive. Because memorization is not my strong suit, I can usually memorize like on the short term, but in the long term, I can't remember just random facts that I memorized like a year ago. And so unless I have a reason or an explanation behind them. And so I am going to encourage you to derive things rather than memorize them. So like speed, if you can remember that wavelength, frequency, and speed are all related and you can use them to derive each other or to convert in and out of one another, then you can actually build this formula for yourself instead of memorizing it. Also, it may be on your reference sheet. You might want to go look at that. Okay, so wavelength times frequency equals speed. And speed would make an excellent conversion factor. It has two units where the top is going to be equal to the bottom or equivalent to the bottom. And you can use it to convert in and out of distance and the inverse of time, or wavelength and frequency. Okay, I did promise we would talk a little bit more about speed before we moved on. So let's talk about speed. Speed of a wave. So if you're talking about a mechanical wave, like energy moving through a medium, like a water wave. A wave on the ocean is energy that is moving through the particles of water, right? That would be a mechanical wave. So if you're talking about a mechanical wave, mechanical waves can be slowed down and sped up, right? If you have a sound wave, it's going to travel at a different speed through air and through water. Sound waves through air are going to travel at a different speed than sound waves through water. And so, depending on the medium that your wave is traveling through, the medium being air or water or metal or whatever else your wave is traveling through, your wave can speed up or slow down. And that's why we have an equation to calculate speed of stuff, right? But if we're talking about electromagnetic waves, which is what we are going to talk about in this chapter because we're concerned about light and how it leads us to electrons. And so we're going to talk about electromagnetic radiation. So electromagnetic radiation can be sped up or slowed down, but not to a very great degree. And so for our intents and purposes, inside our laboratory of room D122, we can't speed up and slow down light. And so we're going to use the speed of light, which is also known as the speed of electromagnetic radiation in a vacuum. And the speed of electromagnetic radiation in a vacuum is always the same. It is 3.00 times 10 to the 8th meters per second. That is the speed of electromagnetic radiation in a vacuum, also known as the speed of light. So this is if you're dealing with light or you're dealing with electromagnetic radiation and they ask you, okay, you have a frequency of, that was wavelength. You have a wavelength of 630 nanometers. What is the frequency? They're not going to give you speed because they are going to assume that you can pull speed for an electromagnetic wave out of your head and apply it to this problem. So fair warning on that. Your book is going to do that a lot. The College Board will probably also do that to you. I believe speed of light is on your reference sheet. Now would be a good time to go look at your reference sheet and verify that and figure out where it is on that reference sheet. Okay, so this is a problem we can do together in class just to practice this. Also, you're going to have a lot of practice of this in the problems in the back of your book. Okay, we talked about this a little bit. I want to step you through how the theory of the atom and how it changed and what was used to change it for a couple reasons. First of all, I want you to understand that the knowledge that we have in your textbook today didn't just appear out of thin air, right? I also want you to understand that a lot of the knowledge that's in your chemistry textbook sitting in front of you is derived knowledge. It's not directly observed knowledge. Even today, when we're talking about atoms and electrons, we can directly observe them in an electron microscope, but even an electron microscope, it's not a direct observation. What happens in an electron microscope is radiation is pointed towards your sample. It bounces off, and a computer detects the reflected radiation and what angle it's reflected at and how fast it bounced back and then that computer takes that information and it builds a model of what could possibly have been there that would have done that reflecting of the radiation. And so it's not when you're looking through an electron microscope and you're looking at atoms and electrons, it's not a direct observation that you're making. It's a deduction based on a human-built computer model. And as we get more evidence and we test that evidence against the theories that we have and the computer simulations and the models that we have, what we find is errors, and those errors and those mistakes and those things that break our theory, they help us to change our theories to get closer to what's actually there, hopefully, to get us closer to being able to predict what's going to happen and observe what's actually there. And so as we talk about this atomic model, it's not crucial that you know names and dates. These are really important people who significantly altered the face of science. But my purpose in talking about this, hopefully, is that you can see the process of science and you can understand the process of science a little bit more deeply. Okay, so when we're talking about the atomic model, there were all these theories way back in the time of like Aristotle and Socrates. There was a guy who stood up. It was Democritus. He stood up and he said, I believe that an atom exists, that all things are made out of these tiny indivisible particles. And he was shockingly close to our current definition of an atom, but nobody believed him. And actually, the theory that took hold was from Aristotle, and it was the theory of the four elements. Everything is made out of, I have to dig deep to my Captain Planet days. Let's see. Everything is made out of earth, air, fire, water, I believe. I think those are the four elements. And so, there were these two competing theories, and Aristotle's theory actually took hold for about 2,000 years. Science moved forward on the basis of this thought that everything was made out of these four elements. And the reason was not because either one of them had evidence. Actually, neither of them had evidence to base their theories on. The reason that Aristotle's kind of took off and the other one kind of died out was because Aristotle had explaining power. He said, well, if a bird is made from more air than earth, and that's why a bird can fly. And a fish is made from more water than earth, and that's why a fish can swim. And so he had explaining power in this theory, and it was kind of taken as truth for 2,000 years. And then in like the 1800s, along comes Dalton. He was about 18. He was in the 1800s, and he was actually a school teacher. And his theory was very close to the theory of Democritus, where he said, everything is made out of these tiny, indivisible, invisible spheres. And so he laid out his theories, and they're called Dalton's postulates. And I think there were 5 of his postulates. And he was right on some of them, and he was slightly wrong on some of them. But the power of Dalton to overcome this theory of the four elements that had been held as truth for 2,000 years was he had evidence. And what Dalton did was he measured masses before a reaction and after reaction, and he measured those extremely carefully. Extremely carefully. And what he began to show that when a reaction takes place, there is no mass that is gained. There's no mass that is lost. The mass that you start with is the same as the mass that you end with. And then he also began to show other things, like when compounds form, let's say a compound forms between carbon and oxygen, it always forms in the same ratio or a multiple of that ratio. So you can have 1 carbon to 1 oxygen, 12 grams to 16 grams, right? Or you can have 1 carbon to 2 oxygens, 12 grams to 32 grams. But you can't have anything in between. You can't have 1 carbon and 1.5 oxygen. And so this oxygen must be indivisible, because you can either have 1, 2, or 3, but you can't have fractions of it. So he started to come out with all of these theories and what we hold to be laws now, based on his extremely careful weighing of reactions, which I think is pretty cool. So Dalton came up with this theory: an atom exists, it's spherical, it's indivisible, and it's invisible. And then along comes J.J. Thomson, and J.J. Thomson worked with what we call a cathode ray tube. And so in a cathode ray tube, what happens is little particles are shot from one side or the other, and the tube is filled with gas, or the thing that's shot is shot through gas, and there he could place charges on either side of it. And what he started to see was, no matter what the gas was, no matter what the source of particles was, that the stream of particles would always bend away from the negative charge and towards the positive charge. So what J.J. Thomson said was, okay, hold up. I'm with you, Dalton, with a couple different things, a couple specifications here. So what I think is, I'm with you on everything is made up of these small spheres, and they happen in ratios, and they're indivisible. But I think there's things inside of them, like negative charges. There have to be negative charges inside all of them, because these negative charges are repelled from a negative and attracted towards a positive. And then a little farther down the line, he concluded, well, if there's positives or if there's negatives present, but the whole thing is neutral, there have to be positives present also. And actually, someone a little bit later, Goldstein, he took the cathode ray tube and he altered it a little bit, and he used it also to provide evidence for protons. And so J.J. Thomson came up with this next model, and he called it the plum pudding model. Right? It's a sphere. They're very tiny, but there are things inside of them. But those things inside of them are all just kind of mixed together like a plum pudding. They're just, think of like raisins inside of pudding, right? They're just kind of floating around haphazardly. They're in there somewhere. We don't really know where they are. And so as you're starting to see this nature of science, as we gain evidence that contradicts a previous model, we don't necessarily toss the whole model out, because there's good things to that model too. We change the model. And then this happened again with Rutherford. So Rutherford, he was the gold foil guy. So he took a source of alpha particles and he shot it towards gold foil. And an alpha particle was thought to be fairly small, and it's also a positively charged ion. It has a mass of 4 with 2 protons. So, I mean, it's fairly small. It has a mass of 4. It's not like gold that has a mass of what, like 79 protons, so like 150 AMUs. I mean, that gold is a pretty big atom, right? And it's also a fairly charged particle, not hugely charged, but it's a little charged. So he's shooting it at this gold foil. He has this detection paper all around it. It's just like one of the old photographs. Wherever light hits it, a spot shows up. And so wherever the alpha particle would hit this paper, they could develop the paper and they could see all the spots where it was hit, and they could, detect where it bounced off. So Rutherford, he was just kind of playing around with alpha particles and shooting it through different stuff. Sounds like a fun job, right? And what they thought was, surely, if we shoot these alpha particles through our plum pudding model, most of the alpha particles are just going to go straight through. And if the alpha particle happens to hit something like a negative charge or a positive charge, that its mass of 4 and its charge of 2 would just blow right through those little tiny particles that were inside the atom. So they just expected everything to hit here. And you know what happened? Most of it did. Like 99%, 98% of stuff just blew right through the gold foil and hit their detection paper right in the back of it. But a couple things bounced back. And that was groundbreaking. Rutherford described it as, shooting a cannonball at a piece of tissue paper. You expect all the cannonballs to shoot through the tissue paper. You don't expect even one of the cannonballs to bounce off the tissue paper, right? But one of the cannonballs, one of the alpha particles, bounced off the gold foil. And so Rutherford knew there was an issue with the plum pudding model. He knew there had to be something inside the atom that was very full of mass and or very charged. Most of the alpha particles blew right through. So maybe most of the atom is space, but there has to be something in that atom that has either a lot of mass or a lot of charge or both that is able to repel an alpha particle. And so Rutherford, again, his evidence changed the model to the nuclear model. So in the nuclear model, what we have, here's Dalton's, here's J.G. Thomson's plum pudding, here's Rutherford's. We have a small, dense, positive nucleus. Electrons are out here somewhere, and the rest of the atom is all space. Okay, so the next life-changing for the atom theory, came from these phenomena that occurred that couldn't be explained. Okay, so we're thinking that the atom has a nucleus. We're thinking it's positive, so all the protons are there, probably all the neutrons too, since it has so much mass. We're thinking the electrons are somewhere, but where are the electrons? What's the structure of the electrons? That's what we don't know at this point in time. And so there were a couple things that were going on that couldn't be explained with the current theory of the model, the current model of the atom. And one was called black body radiation. So in what they're referring to here is, let's say you have a piece of metal, right? Like iron. Think of iron being put into the fire to make a horseshoe or a hammer. That iron is going to start as like a grayish black, slab. And then as you heat it, that iron is going to turn red. And then as you heat it, that iron is going to get hotter and hotter and hotter. And eventually it's going to get really hot and it's going to turn blue. And then the iron's going to get hotter and hotter and hotter. And then eventually that iron is going to turn, white. Okay, so what's happening here is we have a spectrum of electromagnetic radiation, right? And in this spectrum, if you get a spectrum of electromagnetic radiation from the sun and you split it with a prism, what you get is our continuous colors, right? You get red and then orange and then yellow and then green and then blue and then indigo and then violet, right? So the sun is going to give us a continuous spectrum. But our iron, when we heat up iron in the furnace, we do not get a continuous spectrum out. We get red, blue, and then maybe some other colors in there. So what we get when we heat things up in a fire is called a line spectrum. And a line spectrum is different from a continuous spectrum. So if all the wavelengths are there, we would get a continuous spectrum. If all the wavelengths are not there, we get a line spectrum. And here's the problem with this, is if electrons were anywhere around the atom, they could be here or 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 here, we should be able to get any color out of the atom. So the idea is, as electrons move, they fall down, they gain energy, move away from the nucleus, and as they move back towards the nucleus, they lose energy and they give that energy off, right? So as they do that, if we can move the electron anywhere we want to inside the atom, we should be able to get any color out. But what we find is we do not get any color out. We get red, we get blue, and we get nothing in between. So there's a problem with that we can't explain. There's a phenomena that we can't explain with the current theory of the atom. We need to structure the atom differently. We need to add some structure to the atom in order to be able to explain this. And so Max Planck, came up with something called a quantum theory. Well, maybe light or maybe energy exists in quantums. There's little packets of energy. And Einstein jumped in here and he tied it to light. Well, maybe light exists in packets. Maybe light isn't continuous energy like we think of it as. Maybe it actually exists in packets. So one of the things we're going to play with in class is called the photoelectric effect. And there's a simulation we're going to play with that will kind of we'll use it to like hammer out this theory of quantized energy. Okay, so we'll talk about that in class. You can dream about it between now and then, and we'll see what we can build together.